So my name is Justin Vandenbroucke from UW-Madison. The W here is actually not a typo. I moved recently from KIPAC to WIPAC, which is the Wisconsin Ice Cube Particle Astrophysics Center. So this session is called Where Did That Come From? Particle Acceleration in the Universe. So I'm just going to say a few words before handing it over to our first speaker. So the mysteries of cosmic rays are older than the mystery of dark energy and even older than the mystery of dark matter. So it's been 101 years since we've known about cosmic rays. But it's not all unknown. So we have made a lot of progress in those 101 years. In particular, in the last 10 years, just since KIPAC has existed, here are some personal favorites of the progress that we've made in the field in the last 10 years. A GZK-like cutoff was measured, so that could be consistent with that is consistent with the GZK cutoff. It could be the GZK cutoff, or it could be something else. Ground-based gamma ray astronomy has really exploded. So when KIPAC started, there were only 3 or 4 sources known, point-like sources, of TeV gamma rays, and now we're up to 145. So that's gone from sort of a novel technique to a real basic tool of astrophysics. Fermi has made quite a number of discoveries, almost 2,000 sources now. The highlights have really been pulsars, active galactic nuclei. Supernova remnants were believed to be sources. Now they're known to be sources, and also there's strong evidence that they are the sources of galactic cosmic rays. And then, of course, theorists came up with long lists of what Fermi could detect, but even the observers surprised even the theorists. There were some sources detected that weren't expected to be detected, such as novae. The Crab system is sort of our example particle accelerator, and it's also surprised us a lot in the last couple years. The nebula has fast, strong flares in the GeV gamma rays, and with TeV ground-based instruments, we've discovered that the Crab pulsar actually produces pulsed emission to very high energy, even beyond 100 GeV. We can also use these high-energy particles to do basic particle physics and GR measurements. So AGN and GRB, so that's active galactic nuclei and gamma ray bursts, have been used to constrain the nature of space-time and to search for Lorentz invariance violation. While the LHC is shut down to upgrade to 13 or 14 TeV, in the meantime, the Pierre Auger Observatory has used these particles coming from across the universe to measure a cross-section at 60 TeV center of mass. We've seen from Pamela, Fermi, and AMS that there's this unexpected abundance of positrons, and that's a big mystery. And neutrino astronomy, just in the last year or so, is moving from the regime of upper limits to making discoveries. Also recently, we've seen that the Voyager 1 mission is leaving the heliosphere and starting to make cosmic ray measurements in the ISM for the first time. So you can see that just in these last 10 years, we've made a lot of progress on the questions of cosmic rays, and you can see that some of this progress answers old existing questions, and some of it raises new questions. So that brings us to the next 10 years. So I'd like us in this session to focus on what questions we should answer in the next 10 years, what questions we can answer, and what we need to do now to prepare for that. So my personal list of some questions that we can consider, we're going to have time at the end of the session after the coffee to discuss these further. So please start thinking about this. My personal list of questions: do supernova remnants explain the cosmic ray spectrum up to the knee at 10 to the 15 eV? Are there other galactic cosmic ray sources in addition to that? Going to higher energies, where do the ultra-high energy cosmic rays come from? And are they protons or heavier nuclei? We have evidence in favor of each of them. Is this GZK-like cutoff actually the GZK cutoff due to interaction with the CMB, or is it something else going on? There are these cosmic ray anisotropies at 10 TeV and higher, which have been discovered by several different projects, and what's causing that? What's causing this positron excess that's also been seen by several experiments? What's the origin of the ice cube neutrinos that have been seen in the last year or so? These cosmic rays, gamma rays, and neutrinos come from cosmological distances, so how can we use them to probe cosmological questions? And how can we use them to understand space-time? What do we need to understand about particle acceleration to understand dark matter? These cosmic rays and neutrinos can come from dark matter annihilating in the cosmos, but it can also come from particle acceleration, so how do we disentangle those two sources? What other particle physics can we do with these very high energy particles? And finally, do we understand the acceleration processes, and can we simulate them to prove that we really understand them? Finally, from the observational side, what new experimental and observational techniques can we develop? So that's a list to get us started. I think one thing that makes KIPAC special is the way it brings together different communities and different people. So for example, particle physics and astronomy, and cosmology and particle astrophysics. So I think we should also keep an eye out for what intersections there are between our session and the other sessions. So for example, there are natural connections with the dark matter session, and also with the compact object session, but are there other connections? Maybe we can make some connections with dark energy, for example.